Laguerre polynomials are another member of the family of special polynomials used throughout physics, engineering, and applied mathematics. Just like Legendre and Hermite polynomials, they form a structured set of curves that help us describe complicated behaviors in a clean, organized way. What makes Laguerre polynomials unique is the type of problems they naturally fit. Problems involving things that fade out, decay, or weaken as you move farther away from a certain point. They show up in phenomena like quantum behavior inside atoms, the intensity of light absorption, radial patterns in waves, and models of waiting times and probability. Even though their name may sound abstract, the ideas behind Laguerre polynomials are grounded in very everyday physical patterns. To understand Laguerre polynomials, you can picture a set of curves that all begin at the same starting point and then gradually diminish as you move to the right. Each polynomial represents a different level or mode of how something fades out. The first one is very simple and slopes downward smoothly. The next one dips and rises a bit before fading. The next has more humps or oscillations. Higher ones contain more bumps, but still eventually decay to zero. What makes these curves special is that they live on a half line. That is, they start at zero and extend infinitely to the right. Many processes in physics and engineering unfold in exactly this kind of domain. Motion that starts at a boundary, waves that move outward from a point, particles that radiate from a source, or signals that weaken as they travel. Laguerre polynomials are designed precisely to describe this kind of behavior. Most real systems involving decay follow a smooth curve that drops off exponentially. For example, how light fades when it passes through fog, how the intensity of radiation decreases with distance, how the probability of waiting for a long time in a queue declines, how the wave function of an electron in a hydrogen atom falls off far from the nucleus. Laguerre polynomials combine beautifully with exponential decay. When you take a Laguerre polynomial and multiply it by an exponential drop-off, you get a shape that matches the behavior of many physical and probabilistic systems nearly perfectly. This combination creates functions that start strong near the origin, wiggle in a structured way, and then gradually die out. This is why physicists rely on Laguerre polynomials when studying atomic systems, especially the hydrogen atom. One of the most famous appearances of Laguerre polynomials is in the structure of hydrogen's electron wave functions. Inside a hydrogen atom, the electron is described by a wave that spreads out from the nucleus. This wave has two components, an angular part, which depends on direction, a radial part, which depends on distance from the nucleus. Laguerre polynomials govern this radial part. Each energy level of hydrogen corresponds to a different Laguerre polynomial, some very simple, others with more oscillations depending on the energy. These oscillations match the shells and subshells that we learn about in chemistry: S, P, D, F, and so on. The dips and peaks in the radial wave function describe where the electron is more or less likely to be found. Laguerre polynomials provide the perfect patterns for these radial distributions because they allow a smooth decay outward and structured oscillations inward. Without Laguerre polynomials, the hydrogen atom, one of the most fundamental systems in physics, could not be explained as elegantly. Like other special polynomial families, Laguerre polynomials are orthogonal, which means each curve carries a distinct pattern. No polynomial can be built from a combination of the others. Each one captures unique information. This makes them excellent building blocks. When you want to describe a complicated radial or decaying function, you can use Laguerre polynomials as ingredients. A bit of the first polynomial, some of the second, a smaller amount of the third, and so on. Because they are orthogonal, they don't interfere with each other. Each one adds its own flavor to the final function, making approximations stable and accurate. Laguerre polynomials also appear naturally in probability, especially in situations involving waiting times, lifetimes, or decay processes. These scenarios involve random events that tend to happen less frequently as time goes on. The underlying distributions often have an exponential shape, and Laguerre polynomials provide structured corrections that help model real-world irregularities. For example, the distribution of waiting time until the next event in a queue, the lifetime of a component that has a chance to fail unexpectedly, the probability of a system surviving past a certain point. Laguerre expansions allow statisticians to describe these distributions more precisely than using simple decay curves alone. Laguerre-based functions also appear in optical systems. Laguerre Gaussian modes describe how laser beams can twist or carry angular momentum. These patterns, which look like spirals or rings, arise directly from Laguerre polynomials. Signal processing. Laguerre functions help model systems that respond strongly at the start and then weaken over time. Engineers use them to build stable filters and predictive models. Numerical algorithms. Because they behave smoothly and predictably on a half-line, Laguerre polynomials are ideal for approximating functions that decay toward infinity. Laguerre polynomials may seem abstract, but their structure matches the real world remarkably well. They are naturally suited for processes that start strong and fade out. Perfect building blocks for atomic physics and radial waves. Ideal companions to exponential decay. Mathematically stable and clean for computation. Useful in statistics, optics, lasers, and signals. Laguerre polynomials are beautifully structured patterns designed to describe phenomena that decay or radiate outward, from electrons and atoms to fading light, from waiting time distributions to laser beams with swirling shapes. They capture the essence of radial behavior in a clean, organized, and mathematically elegant way. Even without formulas, their purpose is intuitive. They give us the perfect shapes for understanding and modeling systems that diminish as they move away from a source.